Welcome back. We are talking about non-bipartite matching now. And we've established one really important fact in the previous lecture. And that is that we have a characterization of a maximum matching. So in the last lecture, we showed that the following result. A matching is M in a not necessarily bipartite graph, so in just some graph, G is maximum, in other words, maximum size, if and only if there does not exist an M augmenting path. And in the proof from the last lecture, if you look back, you'll see that nowhere did we use bipartiteness. So this holds for general. In other words, not only bipartite graphs. What was special about bipartite graphs that we saw in the previous lecture was two things. First of all, we were able to use this idea to always find a maximum matching because we were able to show that if there exists an augmenting path, it's straightforward to find one. And also, it gave us this nice characterization of when a maximum matching is not integral. When it's not optimal, namely for a bipartite graph, a matching is not maximum if I can find a subset of the nodes for which its edges are non-expansive, its neighbors are non-expansive. So we're going to start with that and give this idea of give the analog for general graphs. And this is also going to start us off along the lines of thinking of how can we develop an algorithm for always finding an M augmenting path, which we know by this theorem has to exist as long as M is not maximum size. So there's the analog to the previous result in the last lecture about the expansiveness of any set in one color class. We can think of that as this Tutte-Berge theorem, which says the following. So let me define some notation first. So for G, our graph, I'm going to use nu of G to denote the maximum size of a matching. So the size of a maximum matching. And remember, we're talking about maximum, not maximal. Therefore, there is one unique size of a maximum matching. And O of G is going to denote the number of connected components of the graph that have odd size. And the reason that is important is that if a connected component of a graph has an odd number of vertices, then the maximum size matching can must at least miss one vertex, since a matching by definition covers an even number of vertices. And therefore, the largest size we could ever hope for a matching to be in a graph is for it to cover every single node except for one node per odd component. And that's kind of the spirit of this result. It doesn't necessarily mean that we have that. For example, a triangle. So a triangle is an example. We have to miss one. But we could perhaps think of examples where a maximum matching might miss two or might miss more nodes. It doesn't mean that we can always cover all but one. And so as a simple example, if we have a graph with one node in the middle linked to many nodes, then of course that graph miss a maximum matching is going to have size 1, and we could have an arbitrary number of nodes. Okay, so the Tutte-Berge theorem says the following. It says that the size of the maximum matching is equal to the minimum over all subsets of V of 1/2 V plus U minus the number of odd components of G once I delete all the elements of U. So for example, if we are able, if we have a graph that has a perfect matching, it must be even and it must be connected. So that means that the number of odd components has to be 0 of the full graph. And I could just take U to be the empty set in this case, and we see that we have equality in this case. So in particular, this tells us that if we have a matching, and if I can find a U that certifies equality here, then we're guaranteed that that this is a maximum size matching. So let me write that down. So what does this tell us? So for M, any matching, if there exists some set U that's a subset of V such that the size of M is equal to 1/2 V plus U minus O of G minus U. Let me put a hat on U just so we know that I'm talking about a specific U. Then it must mean that M is max size. So how, again, where does that come from? Well, we know that M is less than or equal to nu of G. But here what we've shown is that M is greater than or equal to the min over all U, because M satisfies this with equality for a particular U, and therefore it's certainly going to be greater than or equal to the min over all U, but nu of G is equal to the min over all U. So that shows the reverse inequality, that cardinality of M is greater than or equal to nu of G, and therefore it has to be max size. Another nice corollary, so let me even write that as a corollary because it's important to recognize that this is again an instance where perhaps finding a maximum matching is hard. However, if I give you a matching, for you to then certify whether or not this is maximum or not, as far as what we've learned so far in this class, this would require you to check, to certify that there are no augmenting paths. And that's potentially hard to do. You need to check many things. On the other hand, what this theorem tells us is that if I provide you with an M and I provide you with a U for which this is satisfied with equality, those two together, if you believe this theorem, allow you to easily check that the matching is maximum. Because first of all, if I give you a matching, it's very easy for you to verify that it's indeed a matching. And also every quantity on this side is very easy to compute. And therefore we can just verify equality very easily. So this is why this kind of thing is important. Another corollary in the spirit of the result from the previous lecture is that G has a perfect matching if and only if for any U, which is a subset of V, the number of odd components of G, once I delete the edges of U, is less than or equal to U. And again, all you need to do is just plug this back into the result. So let me just even write this as a proof. Plug back into the result with what we know nu of G would have to be if we have a perfect matching. which is just half of the vertices. Okay, so this is where we are, and we're going to spend the next 4 slides proving this theorem. But again, I want you to note that the spirit of it is, in a way, natural. Like when you look at, this is a variational characterization of the size of the maximum matching, but again, it's basically saying that one way to think about it is that the simple idea that a maximum size matching misses one component per per connected component that has an odd number of vertices. That's almost true, but we need to make sure that that's still true for any deletion of vertices. This is one way to think about this. Okay, so let's show the proof. So first, let's show the less than or equal to direction. This is the easy one. So in other words, I need to show that for any u in V, I want to show that, let me flip back, I want to show that the size of the maximum matching is less than or equal to this quantity. And then therefore that will prove the less than or equal to for the min. And so we can just see, so for any u in V, the size of a maximum matching is certainly at most the number of vertices in U plus the size of a maximum matching in what's left. Because so possibly it could be that we could have strict inequality here. Now this in turn is less than or equal to U plus 1/2 of V minus U minus little o of G minus U. And again, this reasoning is exactly what we mentioned in the previous slide. How many edges does a maximum size matching have? It has at most the number of nodes divided by 2, but also I need to subtract off 1 node for every odd component. So that's exactly what this is saying for a fixed U. But then this is exactly the result. This is now equal to, if I just bring the U inside, this is now equal to 1/2 of V plus U. So what happened here? I had V minus U inside, but then I added essentially U, but there's a 1/2 here, so that's why I thought the minus turned into a plus, minus little o of G minus U. And because we proved this for every U, we conclude this inequality. Okay, so now we're going to prove the other inequality, which is a little more, takes a little bit more thought. So we're going to prove this inequality, or really just equality, and we're going to prove this by induction on the size of the vertices. And again, the more we see induction proofs for different classes of combinatorial problems, you'll get a flavor for how this induction works, or how we somehow start cornering what we want to show. Okay, so again, if V has no vertices, or even one vertex, for example, or 2 vertices, it's immediate. So certainly the result is easy for the base case. Now note that because we're doing it by induction, we can also, without loss of generality, assume that our graph has just one single connected component. Otherwise, if it has 2 connected components, then we immediately apply the inductive hypothesis to each part, and we conclude. So, without loss of generality, we assume G has one connected component. Okay, so how are we going to make this? Induction work? Let's suppose there is a vertex which has to be covered by all maximum size matchings. So suppose first that there exists a vertex V covered by all maximum size matchings. So an example is if we have this graph, maybe this isn't that interesting because there's only one unique maximum matching, but in any case, you can see that, let me see, can I make it? I want to make an example where we might have two different matchings. So what I'm saying is that in any maximum size matching, no, I'm failing to come up with an example on the fly, but it's not hard to come up with just under the pressure of the camera. I'm failing. But my point is that if you have a triangle, then there does not exist such a vertex. So because this could be a maximum size matching, and the triangle has only one edge, or this could be a maximum size matching. So there's no vertex that is covered by all maximum size matchings. I'm sure we can modify my example to satisfy my requirement, but in any case, so let's suppose that there does exist a vertex V that's covered by any maximum size matching. It's got to be, it has to be in there. But if that's the case, then we can apply our inductive hypothesis, and that's because what this implies is what is the size of a maximum matching if I delete that vertex V? Well, it's just the size of the matching in all of G minus 1. So make sure that you buy that. And then we can apply induction here and conclude the result. And because we have nu of G minus V is equal to, for some u prime, 1/2 of V minus 1, that's the cardinality of V with one node removed, plus this special u prime that we found, minus the number of odd components in G minus u prime, and minus this V hat this special V hat that we found. And then if we just take u equal to u prime union our special node V that's covered by every single matching, then we see that we have equality for this particular u, which again means that we have nu of G is greater than or equal to the min, and this is what we want to show. So this is equal to nu of G minus V hat plus 1, which is equal to 1/2 of V plus u minus O of G minus u. So we rule out this case. That means that the only remaining cases are the ones where there is not a special vertex that is covered by every single matching. So that means, so thus we can assume that there does not exist a V covered by all matchings. all maximum size matchings. And in particular, what does that tell us? That implies that nu of G is less than 1/2 of V. So immediately this implies that the cases of interest are not ones where we have a perfect matching, because in a perfect matching, every single vertex is covered by any maximum size matching. And again, there might be more than one perfect matching. Just think about the square. So what we're going to do is we will show that there exists an M with M equal to 1/2 of V minus 1. And what does that do for us? This is exactly the statement of the theorem when U is taken to be the empty set. So again, we've shown that the cardinality of the maximum matching for our particular graph that satisfies this non-existence property is equal to the right-hand side for a particular choice of U, namely U equals the empty set, which is therefore greater than or equal to the min, and therefore that's what we want to prove. So let's argue this in a proof by contradiction. So to obtain a contradiction, what we're going to do is the following. Let's assume that this is not true. Okay, so what do we want to disprove? We want to disprove the fact that there is a matching that misses only one node. So the contradiction is, of course, that there's a matching, that any matching has to miss at least 2 nodes. So assume any matching, or in particular any maximum size matching, any max size matching M has M strictly less than 1/2 of V. This is capital V, the set of vertices, minus 1, which means, i.e., any M misses at least 2 nodes. And let's call these nodes something. Let's call them U and V. And perhaps there are many maximum size matchings that miss U and V. So I'm going to choose the triplet. Sorry, not that miss these particular 2 nodes, but there might be many matchings that cover all nodes except for 2. So I'm going to choose M and U and V, this triplet, among max size matchings capital M, so that the distance between U and V is as small as possible. And this is how I'm going to build the contradiction. So that distance between U and V is minimal. In other words, I look at all maximum matchings. We know every maximum matching misses some 2 nodes. They're not going to be the same among all maximum matchings. And I'm going to look for, among all the maximal matchings, I'm going to pick the one where the 2 nodes that are missed are as close to each other as possible. Now, how small could this distance be? Clearly, this distance is going to be bigger than 1, because if they were 1, that means they're neighbors, and therefore I could just add it to the matching. So and that would contradict maximality. So certainly we know that the distance between U and V is at least 2. But if it's at least 2, that means that there is some intermediate node. And so here's my U, and we know that there is some other node, let's call it T, in the middle. So in other words, let's let T, which is not equal to U or V, be a node on the shortest path between U and V. Okay, so we've got now U and V Those are nodes that are not covered by my matching M. We know that those two nodes are as close to each other as possible, but they can't be neighbors, otherwise I could just add it to the graph. And now I've looked at the shortest path between U and V, which has to have length at least 2, so there's at least one intermediate node, and I'm going to call that node T. Okay, so let's try to draw this picture. And so the picture is, here's my matching M, and it misses two nodes, U and V. And there is some other node T that's in the shortest path. Right? So the shortest path between U and V has to go through this node T. So this is what we've got so far. All right, so now I'm going to look at other maximal matchings. So let's let, and how do I know that there is another maximal matching? If there is no other maximal matching, maximum size matching, well, that couldn't possibly be because I already assumed that there is no single node that's covered by every single maximum matching. And in particular, that immediately implies that we can't have a unique maximum size matching, because otherwise every node that's covered by that would have this property. So let's let n be a maximum size matching that misses or does not cover T. Again, how do we know that such an n exists? Well, if it did not exist, it would mean that every single maximum matching covers T, and again, that can't be. How do we know that M covers T? Well, we know that M covers T because we chose U and V to be the 2 points that are as close as possible that are not in M. So if T also were not in M, then we would have chosen U and T or V and T, not U and V. So we know that T has to be in M, so M is not a matching that misses T. But because we assumed that every node is missed by at least one maximum size matching, there's got to be some other max matching out there that does miss T. And I'm going to call that N. And note also that, what do we know about N? We know that since the distance between U and V is minimal, we know that N cannot miss either of U and V. Because if N misses, say, U, then it's missing U and T. But then we have a maximum matching N and two nodes U and T with U and T closer than U and V, and that would be contradicting that distance of U and V is minimal. So that means that N covers both U and V. So in other words, now I know things are a little bit complicated because matchings are edges, but I'm also drawing them I'm writing that they contain nodes. What I really should be saying, I'm trying to say that as much as possible, is that a matching covers a node or misses a node or does not cover a node. Okay, so how does N look? It's, maybe it's something like that. So it contains U and V, but it definitely has to miss T. Okay, so that is N. And again, contains means it covers. It contains an edge which has an endpoint in either U or V. Okay, this is where we are so far. So again, in summary, M misses U and V. Misses means does not cover. N misses T, but does cover U and V. But okay, now what is the other thing that we have to assume? Remember, we said that any matching has to miss at least two vertices. That's our assumption. This is what we want to contradict. So let me just flip back to remind you here. this is what we're assuming. Any matching has to miss at least 2 nodes. We want to contradict this to show that our matching covers every node but one. So if n contains u and v, we know it misses t, it's got to miss at least some other node. So n misses t, it covers u and v, so it must also fail to cover some other node, let's call that x. Okay? Next claim. There exists a y. So let's draw that x here. So let's keep adding to this drawing. I've drawn it outside of n. So this is my x. But now you'll note that I've drawn it inside of m, so you may be concerned about that. Why did I draw it inside of m? But this follows from this claim that there exists a y where the edge xy is in m. In other words, m covers x. Why is that? So think about that and convince yourself that this has to be the case. Okay, so now what do we know? Let me draw that y. So y, I'm going to draw y here. It's getting complicated. This edge is in m here. So now I claim. So I'll write this as a claim here, just to make sure that you think it through. Another claim is that there must exist an edge between y and w in n. So in other words, there's some w here where the squiggly edge has to be in n. Now, why is that? Oh, you know, I forgot to tell you one really important part. I apologize. It hasn't affected anything that we've said so far. It has to do with how I'm going to choose n. I'm choosing n to be a maximum size matching that does not cover t, but I also want to choose n to have as much overlap with m as possible. So, but has maximum intersection with m. And now this is where we're going to use this. So I'm claiming that, first of all, the first claim that says that xy has to be in m. And my next claim is that y has to be covered by n, i.e. y is covered by n. And why is that why is that important? Because if y were not covered by n, if we didn't have this w, right, and that's because if y is not covered by n, then I could just add xy in there. So I could just add xy, and that would contradict the maximality, the maximum size of n. So certainly y has to be covered by n, and that's where this claim comes from. And now we're finally ready to give the contradiction. But now, what can we do? Let's look at, whoops. I didn't mean to, shucks. So what do we have? We've got this is the edge. So I want to look at these nodes here, W, Y, and X. And the first claim says that XY is an M. The second claim is that YW has to be an N. But this is a contradiction because we can do the following. N minus the edge between Y and W. What does that allow? Well, if I take away that edge, then now I'm free to add in the YX edge. And what is this going to contradict? And so again, let's take this one at a time. I couldn't add YW. I'm sorry, I couldn't add XY to N because that would contradict the maximum size of N. So we had to assume that Y is covered by some other edge, YW. But now I can just swap YW with YX. And what does this contradict? So this is a maximum matching that misses T. And now this is the point that I forgot to say initially here. Among all maximum size matchings N that miss T, we chose the one that has maximal overlap with M, but we just chose one that has a larger intersection. So there's a number of steps, and this is our contradiction. So the contradiction proves the result. So again, there are a number of steps here, but each one of them is straightforward if you just follow through the reasoning. And it's important to see how everyone follows from this pretty simple assumption that says that there is no single node that is covered by every maximum size matching. Everything else basically followed from there. So let's flip back to the statement of the theorem so we can wrap up and see what we proved. So we have now this characterization of optimality. In particular, if I give you a matching and I produce a set U, and you verify that this equality holds without the min, of course, then this theorem guarantees that there is it guarantees that there is that your matching is maximum. And so this in a way it's nice because it provides us an easily computable characterization of optimality, different from saying that there does not exist an augmenting path, because that actually takes significant work to try to show. In the next lecture, we are going to move to exactly that, trying to find an augmenting path.